Looks like we're actually 1 minute late to start the session. So I'll get Joel to step up here and take over the screen share for me, and we'll get going.
All right, you can see the slides?
Yes, we can see it. Take
Awesome.
it away.
All right, thank you. So a couple years ago, we proposed this method to find apps that were using side and covert channels, exploiting them in practice among smartphone apps by basically running the apps, seeing the network transmissions that are being sent, and if it was protected by a permission, like location, and it didn't have that permission, flag it for further analysis. And this method was somewhat successful. We found, for instance, an app that was reading the ARP cache to get the router MAC address. It didn't have location permission, and you need location permission to get the MAC address of routers because the internet basically knows where all the routers are, and they don't typically move around a lot. So these MAC addresses and SSIDs have become a surrogate for location. We found that another app was wholesale uploading all of your EXIF metadata because it was classy like that, and it included latitude and longitude as part of just geotagged images, which we saw being sent. Baidu was saving the IMEI to the SD card, so the same SDK from Baidu in another app that didn't have permission to access IMEI could read it out. And the advertising company / game engine Unity was using an ioctl to get the MAC address of the device. So the device MAC address, it's not a location surrogate anymore, but rather this becomes a sort of unresettable super cookie to just track users, a serial number burned into your device that you just can't change. And in fact, Android since version 6, so 2015, has not allowed apps to get the MAC address of the device for this particular purpose. So this method, though, keeps giving us new results. So here I'm going to talk about 2 new findings we've made and 1 variation of a theme that we saw before. So the first one comes to us from CNN. CNN is an American news-based entertainment company, and we saw them transmitting a payload of data to claspws.tv, this chunk of data. And when you do this sort of analysis enough, you just see the beginning EY capital J, that's base 64 for JSON object. So the first thing you do, base 64 decode it, get a JSON object, and when we looked at it, we can see that sure enough, there's the SSID of the device being sent out over the network, yet the location data was not present. It was unknown. So the app, in fact, did not have the location permission, yet somehow it was accessing the MAC address or the SSID of the router that it was connected to, so location surrogate. So we looked at the app to see how it was doing it, and normally when you look at an app, it's obfuscated. So all the variables are replaced with A, B, C, and stuff like that. Whereas in this one, it wasn't. The developer human meaningful variable names were still present. And the one that was responsible for setting the field in the JSON object was called hacked SSID. So a developer wrote at some point string hacked SSID and semicolon. And so now the question is, how is this filled out? So it turns out there was a specific Android Pie network manager class they had created to circumvent the permission system on Android Pie, because earlier they didn't need to, but as of Pie, they needed to. So they had a special workaround to circumvent the permission system. And they used effectively a network callback. So they found that there's this network capabilities callback. When the capabilities changed, a callback function is invoked. This is from just the Android developers. And it happened to be that one of the fields in the callback, there was an extra data field. It contained the SSID. This was an oversight. It shouldn't have had that. And so we were able to responsibly disclose this and get it repaired, and got a CVE and a bug bounty. And it is unfortunate the developer who discovered this didn't follow the same route and chose instead to exploit it, but that is how it is. Our second example comes to us from dev to dev. And so if you're like me, you've also never heard of them. So to give an introduction, they are a comprehensive solution that analyzes your apps and games and gives you valuable insights. And so one of the things that they send is the device MAC address. Again, this super cookie, this unresettable identifier tied to the device. And any transmission of this is not allowed as of Android 6 and higher. So this in itself represents a violation of the permission system. So how is it obtaining this information? Well, the first thing we did was we grepped for the string inside the program, and we see what we don't want to see, which is basically a giant 20 megabyte binary object is the one that contains the string. So reversing it will be a little more challenging. We look inside, and it's just a string next to all the other strings. It occurs 2 times in the same story each time. So we have a challenge ahead of us. But thinking back to how we looked at Unity and its use of an ioctl, if it's happening in native code, if this access to the MAC address is happening in native code, it's going to either be a system call or it's going to be somewhere in libc. So we can just instrument those things. So we go to the Linux operating system, we find the implementation of ioctl, and we add our own little instrumentation. No, it's not happening in ioctl. Okay, what about get sockopt? No, it's not happening there either. And then we stumble across this function getIfAdders. So getIfAdders returns a linked list structure, and one of the fields happens to be the MAC address of the device, of the hardware interface. Now this particular function is not in POSIX. It comes to us by way of BSD, but in the BSD implementation, if there is a IP address, it does not provide any link layer information like the MAC address. So in the Linux implementation, it does, and this is how they were able to get the MAC address of the device. Or at least at this point, this becomes a possible way. And so we wanted to confirm that this is indeed the way that they were doing it. So we go to the implementation and we modify it. And what we do is effectively make the MAC address a palindrome. We just make it conspicuous in some way so that we know that indeed this is the code path that it went through in order to perform this exploit. And sure enough, when we looked at the network transmission afterwards, we see that our conspicuous MAC address is as we had designed it, and so can conclude, yes, this is the route that they are using. Now, there's another interesting thing about dev to dev that I want to talk about that came to light as we were doing this analysis. And this has to do with the advertising ID. So if you have an Android phone, you'll have an advertising ID. And you can see here, this one begins with CED at the beginning. And maybe you don't want to have your advertising ID being able to track you across apps while you're using your device. Maybe you just you don't want it, so you want to opt out. So there is an opt-out of ads personalization. You can press the button and it sets it to blue. However, this really has no consequentiality in terms of accessing the advertising ID. It's more like the don't be evil bit being set. Because all it does in many of the network traffics that we've looked at, it just sets the is limit ad tracking enabled to true or do not track as true. And yet the advertising ID seen at the top, the CED, it's still there as well. So it's effectively saying to the company, here's the user's identifier, but don't use it in any context. Don't use it for behavioral advertising. Don't build a dossier. Just don't use it at all. So maybe that's not the best way to implement this. So what about the other option you have at your disposal? You can reset your advertising ID. It replaces it with a new random number. So now we have one that begins with 380. So the idea here is your new identity is unlinked to your old one. There's no connection between the two. It's a truly random number. And now going forwards, all of your new transactions will be with this new number. Now, this would be great if it happened every minute instead of being deliberate action under 5 layers of menu, but still, it's the best that we sort of have. However, dev to dev found a workaround, which is to just send both. And it even calls the old one prev in the HTTP query argument, sending the old advertising ID, prev equals the one beginning with CED, and the current one, UID, the one beginning with 380. And this occurs after rebooting the device, meaning that they must save it somewhere on the device to actually remember that this was, in fact, the old advertising ID. Our final example is from the dub music player. So suppose for some reason you wanted to listen to dub music, then maybe you have this app. And if you have this app, then you'll be talking to measurelib.com. And in this particular example, they're sending a 28 kilobyte gzipped upload of post data to mobile.measurelib.com. So what are they sending? Well, the bulk of it is a complete dump of all of the apps that you have installed on your device, all the permissions they require when they were installed, when they were updated, including the full file system directory path where they're located. And that's bizarre, but all right. And they are also sending, more relevant for our purposes, an ARP survey where they included the router MAC address. Again, this surrogate for location. And noteworthy, they did not have the location permission, so they should not have been able to access this value at all. Now, so you might be wondering, why report all this? Why are they collecting all this? Why report it? And indeed, they even purport to answer that, why report? But their answer is not very satisfying. They say because the app launched. Or a little bit later, why report? Because report interval expired. All right. Well, not quite a satisfying answer, but still interesting all the same. So how did they get the router MAC address? Well, when we looked at other traffic coming from this app, we saw that it was doing a plug-and-play discovery on the home network, sending out a broadcast message to all of the devices nearby, asking for configuration details. And sure enough, the router happily replies back. And part of the reply in the UUID, the node component is in fact the 48-bit MAC address being sent back. And you have to remember that these apps and all of the third-party code that's included, they're running in the trusted part of the home network. The firewall exists to keep the bad guys from the outside from getting in, but once you're in, you're free to chat with the router, it seems. So we wanted to understand what was happening and where this code was occurring. So we do our searches. We grep for measurelib, couldn't find it. We grep for Wi-Fi MAC, couldn't find it. We grep for Y-report, couldn't find it. So something bizarre is happening. There's no evidence of any of the strings that we saw being anywhere in the code. So our trick to then is to find other apps that happen to be running the same or communicating with the same domains and seeing what code they have in common. Because at this point, it could be any of a number of SDKs in this app. The search space is huge, but here we can winnow it down to just the specific third-party library that happens to be in all of these other apps, which we find is this one called Coolest Library. So we start looking into who's responsible for Coolest Library. And what we find is literally 5 results. And 2 of them have malware in the title, so not a very good sign. But after some investigation, I believe it was a sort of Stack Overflow style question and answer site where a developer was asking for help integrating this library. We managed to find an unlinked website that had the information from the provider of the library, including how to integrate it. And going to their website, we find that it is a Panamanian company called Measurement Systems, the Internet Measurement Authority. And not much other information can really be learned about this particular entity. But what about its strings? So why were all of those strings not present? Well, going into the Coolest library, we look for the strings and we find that they're all base64 encoded. Okay, well, maybe that's why. But when we base64 decode them, we still don't see anything that we're looking for. We still don't see Y report. So looking at the code, what we find is that every time a string is used, it is passed to this d.g function. And this d.g function takes a string, returns a string, and the return value is the key in that JSON object. So whatever is happening in d.g is what we're after, is explaining this mystery. So I won't go into the full details of it here, but here's a faithful representation with my own interpretation of what the variables are for the d.g function. First, they base64 decode it. Then they construct a password out of 2 parts, a static function returning Mia and another one saying sure to create the word measure. They do the same with the salt to create measure, move, measure. They do 10 rounds of password-based encryption. They then get a static IV and use AES in CBC mode to decrypt the actual string. And it's great that they're only using 10 rounds of password-based encryption here because this is happening for every single string for every single time is ever being used to create this 28 kilobyte JSON object. Every single time, no caching at all. But these sorts of techniques do slow down the sort of analysis that we do because string search is really the first step towards understanding what's actually happening inside these libraries. So thank you very much for your attention. These sort of stories I've been meaning to put on our blog.appcensus.io. And so now maybe I'm a little more motivated to actually get these written up. But we have other stories there as well that we report from our findings and try to target it somewhat at a high undergrad level for a security style course. So teaching some of the security concepts as we go along. One of the ad networks, for instance, using frequency analysis to do break a Vigenère style cipher, like these sort of things sort of work. And so we detail these stories in our blog. Thank you very much.
Okay, let's thank Joel. And our next speaker is Eleanor, who's going to be talking about some legal stuff to complement the. We should have had you actually the first speaker after the keynote, given the tie-in, but it is what it is. So take it away. I do not hear you. You are muted.
All right. So please continue chiming in if at any point you cannot hear me or you cannot see what you think is an appropriate thing to be seeing at that point in the talk. So today I want to talk about some work that I've been doing with my research lab over the last year or so, looking at CCPA, the new California privacy regulation. And this is work that I did with two of my students at Pomona College, Sean and Aiden, and also with Ryan, who was a high school intern with my group last summer and is starting an undergrad at UC Berkeley this fall. And the starting point of this work is that, well, Pomona College is in Los Angeles, California. So when I first moved out to LA about 3 years ago, I was really excited to discover that California was in the process of just signing into regulation a new privacy law. And so last summer, shortly before it went into effect, I thought it'd be fun to look and see what's going on with that law and how much privacy are people going to actually get. At the time, I'd been hoping that a little over a year later, I'd be able to stand in front of a room with all of you in person and give you this talk, clear and conspicuous, the right to opt out of sale under CCPA. Unfortunately, that went wrong in a couple of ways. First of all, as many of you have probably noticed, we are not in person. Second of all, I don't feel like I can honestly give you this talk. So instead, I'm going to give you a slightly different talk called Unclear and Inconspicuous, the right to opt out of sale under CCPA. So to get started, what is CCPA? If you've been hanging out in certain circles, there's been a lot of discussions about CCPA over the last few years. And a lot of them boil down to this idea that CCPA is basically GDPR, but for California, or but for the United States. Well, okay, they're both privacy regulations, yes. And there are actually a number of distinctions between the two laws that result in different behaviors. So I think it's worth taking a look at CCPA and seeing what exactly we're getting out of this law in particular. So CCPA is the California Consumer Privacy Act. Like GDPR, its idea is to give users more control over their personal information. And this comes to light in 4 different rights that California users now have. They have a right to know what's being collected and what's being done with their data. They have a right to delete certain data, particularly if it's inaccurate. They have a right to opt out of sale of their data. And they have a right to not be discriminated against, not be retaliated against, if they choose to invoke their rights under CCPA. And this was signed into law in 2018, and enforcement for this law began last summer. So this work is focusing on this 3rd right, this right to opt out of sale. What's this right to opt out of sale and what is it about? Well, right to opt out of sale is about giving users the right to opt out of sale of their personal information. One of the interesting things about this, though, is the definitions of these. Personal information is very broadly defined. It includes anything about a person or anything that could reasonably be linked to an individual or a household, including things like browsing history, your interactions with websites, your interactions with ads on websites, all of that data that we know companies like to collect. And sale is also broadly defined. It includes selling, but also renting or making available any of this information to businesses in exchange for money or any other valuable consideration. And if companies do any of this, they have to give a clear and conspicuous link on the homepage of their website. And more precisely, that link needs to be called "Do not sell my personal information" or "Do not sell my personal info." So this sounds good. This sounds like we're going to get a lot more privacy. We're going to be able to prevent companies from selling our data, and we're going to be able to find these mechanisms and life will be great. Of course, when we started doing this work, there were no actual numbers on how good we could expect this to be. But we can draw some analogies to some other sorts of interactions that we've seen. One example might be the Apple's transparency tracking opt-in that they introduced in iOS 14.5 this spring. There are a number of different metrics about exactly those opt-out rates look like, but it's approximately 58% of users are saying this app should not track me. They're opting out effectively of tracking on mobile apps. Of course, if you've used this particular feature, you're probably thinking this is not a great comparison to something like CCPA, which is true, because these applet interfaces actually pop up in the app, and you have to click yes or no. So maybe a better comparison would be looking at cookie banners in Europe. If you look at cookie banners, well, there was some really nice work in CCS a couple of years ago that looked at what the opt-out rates were for cookie banners after GDPR. And they found that the opt-out rate varied a lot depending on the exact design choices and the locations, but for common implementations, it was somewhere around 4.5%. So we imagined we could see something somewhere in that range for the rate of opt-out of sale for our users. But we wanted to find out. So we implemented a browser extension that for each website you visit, automatically detects whether there's a link that will allow you to opt out of sale. And every time a user visits a website, it logs a hash of that website, and also logs whether or not they click on that link. And we recruited 22 users to install this browser extension and sat back and watched for a week what they did. And at the end of the week, we discovered the total opt-out rate was 0%. Not a single one of our users had opted out of sale on any of the websites they visited. So why does that happen? Well, in order to see why that happens, let's play a game. And let's play a game I like to call Spot the Opt-Out of Sale Link. So I've got a couple of examples. If you're at home now, you can play along on your own. If you're in California, this will definitely work. If you're in some other jurisdiction, unfortunately, I haven't tested it, although I'm curious to know if it will. Otherwise, we can play along together. So let's take a look at this first example, ESPN.com. Here's the homepage for ESPN.com. Can you spot the opt-out of sale link on this page? You can look around, look along the top of the page, look along the sides of the page. Of course, to be fair, I'm not showing the whole website, so I can scroll down a bit. No, I can keep scrolling. At this point, you've probably seen a bunch of websites, so maybe I should scroll all the way to the bottom. Scroll all the way to the bottom, scroll all the way to the bottom, and then I will discover at the very bottom of the page, there is a link saying, do not sell my info. And you can ask yourself, is that a clear and conspicuous link on this homepage? Here's another example. Here's the homepage for BuzzFeed. And you can say, all right, can you spot the opt-out of sale link on this homepage? At this point, you're probably going, I'm on to you. Just scroll down to the bottom. Okay, I'll scroll down to the bottom. Scroll, 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 scroll. Load more. Okay, I'll load more. Scroll, 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 scroll. No opt-out link. So in the interest of keeping within the time limit, I'll give you a hint. You go up to the menu at the top and then go and look down here. You'll see a link that will allow you to opt out of the sale of your personal information. And so you can ask yourself, is that a clear and conspicuous link that will allow people to opt out of sale? And you might be wondering at this point, did I just cherry pick those two examples? And well, yes and no. I didn't pick them at random, but they're actually pretty representative of the sorts of things we see. So in order to figure this out, we ran an observational study where I had my students look at the top 500 US websites and figure out what do their opt-out of sale mechanisms look like. And we coded them to see, do they sell data? And we specifically were looking at whether they sell data under CCPA, because you see a lot of things like, we don't sell personal information, but technically under California law, we sell personal information. So we're looking for whether under California rules they were selling it. And if they were, what sort of link did they have? And in fact, we did this not once, but we did this 3 times. And we discovered 2 things. One is that, well, at this point, I'm now my students' favorite person ever, and they all absolutely love me, having had to look at 1,500 websites. But also, we have some fresh off-the-press results from what enforcement looked like in the first 2 weeks after the law was passed, what it looked like 6 months later, and what it looked like a year later, meaning in the last couple of weeks. And what we see is that only about 8% of websites have banners like the cookie banners you see in Europe. 80% of websites just have a link, and some of the websites don't even have that. Maybe they have a link on their privacy policy. Remember, the link was required to be on the homepage, or maybe nothing at all. And to make this worse, a lot of the links are not visible. Here at the very bottom, in the dark color, you'll be forgiven if you can't see it, because it's really small, it's under 2%. You see the number of links that are actually visible when you initially visit the page. The vast majority of links are only visible after you scroll down to the bottom of the page. And a small but increasing number of links, like the BuzzFeed one, are only visible after you click on some menu or expand some sort of clickable interactive element, and sometimes do that and scroll to the bottom as well. So you could ask yourself how bad that is, and we ran a user study to figure out how bad that is. We built a website. We had a version of this website that just had links, and then we had a version with banners, because prior work says that different banner locations have impact in terms of exactly what the opt-out rates are. We had lots of different versions of banners, banners at the top, banners at the bottom, banners in the corners, banners in the middle. And then we put this website up and ran a Google Ads campaign to get a bunch of users and watched what they did. And what we saw was that for the banner versions, about 15 to 18% of our users were choosing to opt out. But for the link-only versions, you're down under 2%. And this is a real difference between the opt-out rates we're seeing for CCPA and for things like GDPR. It actually gets worse. We ran a version of this with users that we recruited from Mechanical Turk instead of through ads, so that we could ask them some follow-up questions. And there were some interesting results here. In particular, we discovered that 45.5% of the users who saw the link-only version of the site weren't even aware that they had an opportunity or had a right to opt out of sale of their information. So this is disappointing. This is not what we wanted. This is not what we hoped for. This is not the sort of privacy-enhancing technology we would like to see as a result of legal regulation. And that's just to click on the link. There's a bunch of stuff about what happens after you click on a link. Some cases, there's a single button just to opt out of sale of personal information. Although in the interest of full disclosure, this particular single button shows up after a whole bunch of text and you have to scroll down to see it. And if you do click on it, a follow-up alert comes up that says, "Are you sure you mean that?" You also see versions with 2 options, often toggles, but there are other versions as well. See versions with more options, lots of different purposes or people they sell things to, or even more different options. You'll also see forms where you have to fill out personal information in order to opt out of the sale of your personal information, and instructions for sending someone an email or changing your account settings or changing your browser settings and things like that. In the interest of not going over my allotted time, I'm not going to go into a lot of detail about exactly what we saw here. We did see the sorts of things where maybe not the most privacy-enhancing design. There's been a lot of work on nudging and dark patterns by other people. That's really awesome. We're going to see a lot of nudging and dark patterns in this context as well. As you might expect, simpler you can get. 1 button opt-out only is going to have the highest opt-out rate. 2 buttons lower than that. If you use nudging, highlighting, and other things, it goes down a bit. If you make it more inconvenient, multiple options, or require a form, it goes down even more. I don't want to run too far over time, so I'll just give you the TLDR. Disappointing, but not actually that surprising. So where does that leave us? What we're seeing is that there are a lot of steps individual websites can take in order to enhance privacy. And so if you're running a website and you care about privacy, you can do pretty well just by designing and implementing something that works for typical users. There's also probably room for a lot of space to develop privacy-enhancing tools that can complement legal regulations. So for people who work in privacy-enhancing technologies, this is probably great for a lot of us. In follow-up work, one of my students and I have implemented a browser extension that automatically detects links and converts them into banners. So if cookie banners are everything you ever wanted in life, which I really hope they're not, but if cookie banners are everything you ever wanted in life, then this is the browser extension for you. You can also think about what are the higher level takeaways. We've been looking a lot as a community at GDPR. And this work and some other work by other groups has been looking at CCPA. There are lots of other regulations around the world and in the United States, both ones that have been in action for a while and ones that have just gone into enforcement, ones that are coming through the pipeline, and ones that are under discussion now. So we need robust enforcement mechanisms. We need to talk about more than just requiring a link.
We are learning of different players going abroad, players who don't really have great resumes within Major League Soccer, but they're banking on their potential.
I'm going to stop there.
Talk about potential. You know who saw potential in him? Dabo Swinney, the Clemson head coach.
Okay, let's thank Ellen here.
Had a soccer
I'm
scholarship.
not sure who's watching sports right now. Okay, they seem to have muted. Okay, so we have one more talk to go. It promises to be an interesting one. We have Martin Kleppman, who's going to talk about cryptographic backdoors. So take it away, Martin.
Hello, everyone. Just a minute, let me share my screen. Okay, can you see that? Can you hear me?
Yes, we can see that. Yes,
Okay,
and we can.
great. Yeah, so this is probably going to upset a lot of people in this community. Maybe be a bit controversial, but I'm really interested to see what the discussion is after this. So, you know, we've heard the story a million times before. Law enforcement and various politicians say it's terrible that we have these systems that are end-to-end encrypted because terrorists are going to use it, child abusers are going to use it, and it means we can't do our work, and we have to weaken these end-to-end secure systems. To which, of course, the response of the information security community is, no, we must never do that. Security is bad enough as it is, even without deliberately weakening it. Or maybe even saying, well, cryptography is just math and you can't ban mathematics. Whatever the arguments are, I'm not going to rehash them all because you've all heard them a million times before. What I will observe is that, well, my personal opinion is that saying something like cryptography is just math is not going to be very helpful, because this is essentially saying we can ignore whatever laws are passed around regulating cryptography because, you know, people can just implement it themselves if they want, which I don't think is really true, because in the end, the authors of software are subject to the laws of the jurisdictions in which they live. The same is true of the users of the software. The same is true of the providers of the servers that the software uses, and so on. So software is fundamentally still subject to laws in various jurisdictions. Of course, if bad laws and bad regulations are proposed, we can and should campaign against those. But I think simply ignoring it and simply being stubborn is not going to work. I think it is going to be more productive if the information security constructively engages with law enforcement and at least explores whether there's a middle ground that we can find where law enforcement can do their work within the realm of protecting civil liberties, and at the same time, the vast majority of users who are using technologies for honest purposes can enjoy privacy. So right now, the way that law enforcement gets around end-to-end encryption in systems is, well, either they use 0 days to get root on a device, and then of course they can do anything. Or one of the newer ideas is to have a concept of ghost users, where rather than a cryptographic communication, secure communication between two users, the intelligence agency gets added as a secret extra end to the end-to-end communication. Of course, these are both terrible in terms of security because they are they're totally unaccountable. There's no way of figuring out whether the way that law enforcement is using these capabilities is actually in line with the law. And there's no way of knowing whether they are used only in specific cases or for mass surveillance. So I think what a better approach would be is to say, actually, we can have a backdoor in end-to-end encrypted systems, as long as this backdoor has safeguards built around it, and those safeguards are both technical and legal, to ensure that it cannot be abused, at least not without being noticed. So in particular, what we want to do there is prevent this being used for mass surveillance. And so here's a proposal of a type of backdoor that I think would achieve this. It's quite simple. I think it's fairly straightforward, although I haven't actually seen it proposed anywhere before. It's entirely possible, though, that I've missed it, somebody else's proposal previously. So we start with a law enforcement agency who go through the usual legal process. They have some case where they want to investigate a subject. They go to a judge or suitable authority, and they get a warrant or a subpoena or something along those lines, which gives them the authority to request some plain text of some encrypted communications. With that, they go to the service provider. So this would be Facebook in the case of WhatsApp. And now here comes the proposal. So the service provider maintains a transparency log, very much like certificate transparency. And all of the entries in this log are totally public. Anyone can see what they are. When the service provider receives a warrant, they add a new entry to this log. The details of this entry I'll explain in a moment. And this log is now read and followed by, anyone can do it, but I'm going to assume that some organizations that promote civil liberties, such as the ACLU and others, they will act as auditors of this log, and they will track it, and they will report summary statistics to the public in order to let the public know what is happening, what sort of warrants are being served on this service provider. So let's look at the contents of one of those log records. So I suggest that the contents should be, first of all, the jurisdiction of the warrant. That's very important to know from which jurisdictions the service provider is accepting warrants, because a warrant coming from the US is not going to be the same as a warrant coming from, say, the Saudi Arabian government or something like that. Then, secondly, a code indicating the reason for this warrant, which might be terrorism or child sexual abuse or whatever it is. Validity start and end date. And then it does not contain the target of the warrant, but instead it contains a cryptographic commitment to the device ID that is the subject of this warrant. And so this means anyone who's just reading the log publicly can see that there is a warrant, but they can't see who the target of the warrant is. However, it is possible for the service provider to reveal this cryptographic commitment in order to show that a particular device ID is in fact the target of this warrant. And importantly, a particular log entry can have only a single target. Now, in order to activate this backdoor, what happens is that after the service provider has appended this entry to the log, they now send a message to the device of the target user who should be investigated. They send the log entry, they reveal the cryptographic commitment for the device ID to prove that their device ID is the one in the log entry, and they include a cryptographic proof of the fact that this log entry is in fact included in the log. And the target user device checks this silently, and if it all checks out and it's all correct, then the user device simply takes a copy of whatever user data is on the device right now and uploads that to somewhere where the law enforcement agency can access it. And this upload continues until the expiry date of the warrant, and then it stops. And so the key idea here is that anyone can see the number of warrants that are being issued, because you can only have a single device targeted for each entry in the log. The one extra thing we can add here in order to improve our confidence that this is being done legally is that there's a trusted oversight board which checks every entry that the service provider adds to the log, and the service provider also gives a copy of the warrant to this trusted oversight board, and the board checks that the warrant is genuine and is legal according to the laws of the jurisdiction in which this is all happening. So uploading a plain text copy of your data sounds like a ridiculous proposition, but this is in fact exactly what a lot of end-to-end encrypted messaging apps in fact do already. So for example, WhatsApp and iMessage have this cloud backup feature in which, or the entire point of the end-to-end encryption is really undermined by just taking a copy of your messages and uploading them in plain text to a server. So the only effect of this backdoor is essentially that if the user has disabled these cloud backups, then activating the backdoor means the backups get silently re-enabled. Let's talk briefly about the characteristics of this proposed scheme. So first of all, I think mass surveillance would be very difficult to conduct using this system because it would result in millions of log entries. And so this would be immediately obvious to anyone who's tracking the log that there is mass surveillance going on. So it doesn't prevent it, but it means that mass surveillance would be immediately discovered and would be subject to public debate. In the scheme, there's no key escrow, there's no golden master key that can encrypt, that can decrypt everything. So all of the problems that would come with having such a master key simply go away. There's no change to the actual cryptography. The protocol is really simple, actually, so you can explain it to people who are not very technically sophisticated, and they will still be able to understand it. One characteristic of this protocol is also that if something is deleted from the device by the time the backdoor is activated, then the law enforcement does not get a copy of that data that has been deleted. I think that's reasonable because if the law enforcement agency went and physically seized the device instead, they would also not get a copy of any data that has been deleted. So what they're getting with this backdoor is equivalent to what they would get by physically seizing the device. I think that's a fair compromise. If law enforcement wants to hide the fact that precisely when these warrants are issued, you could add fake entries to the log and publish the log entries on a preset schedule in order to avoid leaking this timing information. And finally, as I said earlier, I think it's very important to make explicit which jurisdictions are allowed to, or are going to be have their warrants accepted by the service provider and which jurisdictions will be ignored. You might now ask, well, is law enforcement going to actually go for a scheme like this? This is a very fair question. I did find an interesting article from two technical directors at GCHQ from a few years ago, where they argued the principles of what they call exceptional access capabilities, in other words, backdoors, what capabilities that should have in their opinion. And they said very explicitly they do not want key escrow. They call key escrow catastrophically dumb, literally. So they do not want any mechanism that would allow them to decrypt all of the communications in bulk. They specifically want a mechanism that can give them access only to specifically targeted users and not to anybody else. And secondly, they are actually happy with this idea of having a public audit mechanism that demonstrates to the public that the backdoor is only being used at a small scale for a small number of specifically targeted suspects and not at large scale. And so they are actually very happy to have this kind of degree of transparency that would be implied in the kind of log that I suggested. So that's it, essentially. I imagine there's going to be a lot of disagreement with this, but I'm very curious to hear what folks think about this.
Okay, thank you very much, Martin. Let's thank all the speakers, and we have half an hour to discuss. I have a feeling lots of people will have lots of opinions to share, so please share them.